This is the post-optimal analysis. So in lecture 8, we dealt with the sensitivity of the optimum solution. We determined the ranges for the different LP parameters that will keep the optimal basic variables unchanged. And this is lecture 8 was the sensitivity analysis lecture. In this lecture, or this part of the lecture, we deal with making changes in the parameters of the model and finding the new optimal solution. And I'm going to refer back, just make sure that you make those notes. And I'm going to refer back to the example, the TOEIC example. In which we were trying to determine how many trucks, trains, and cars we should produce for this toy company. And we have the constraints for the operations and the number of hours per operation that we have available. And we were trying to maximize our revenue based on the revenue per product. So we have the problem. And if you solve this problem, the optimal solution, as we saw already in class, is $1,350 when you produce no trucks or no trains, 100 trucks, and I believe was cars, 230 cars. That's your optimal solution. That was the answer for that question, for those questions. Okay, so now I want to find the dual for this problem. So let me write the dual. So again, we follow the same concepts. We have a maximization problem, so now we have a minimization for the dual. So minimize z equals 430 y1 plus 460 y2 plus 420 y3. So you know that you need to define a dual variable for each constraint. Okay, so I have a dual variable for first constraint, for the second one, and for the third one. And from there you just multiply the right hand side times that dual variable, and you get the objective function. Okay, and that should be W, sorry. So you're taking the right hand side and you're constructing the objective function for the dual using the right hand side. Now, let's write the constraints. So subject to y1 plus 3y2 plus y3 greater or equal to 3. Then we have 2y1 plus 4y3 greater or equal to 2, and y1 plus 2y2 greater or equal to 5. y1, y2, and y3 greater or equal to 0. And the optimal solution is y1 equals 1, y2 equals 2, y3 equals 0, and w equals, yes.
Why y1, y2?
Oh, yeah. I skipped one step here, and I apologize for that. I needed to make this equalities first. So you remember the first step was to make this an equality and then move to the next So let me see if I can construct this really quick. So x1 at the end is going to be the same answer, 2x2 plus x3 plus x4. I guess you don't need that one. Equals 430. Then you have 3x1 plus 0 plus 2x3 and then you need to add some extra constraints here. So at the end you will see that how that will become y3 equals or greater 2, because this x3 now will become an extra constraint. So it will be y3 or y2 greater or equal to 0. Should be. It will be y4. y2 greater or equal to 0 and y3 greater or equal to 0. Okay, so that is why that becomes this. Again, I don't want to confuse you. So the first step you always need to do is to make this an equality. Remember? Because those constraints are less than or equal. Okay, so that's what I'm doing here. I'm adding those slacks and making those constraints equality. Okay, once you have that in equality form, then you move and construct the goal. So from here, you go to here. So you start with y1 plus y3, y2 plus y3 greater or equal to 3. Then for the second constraint, you have 2y1 plus 4y3 greater or equal to 2. For the third constraint, you have y1 plus 2y2 plus 0 greater or equal to 5. Then you come to the slack variables. You have y1, you have no coefficient for x4 in your objective function, so that makes y1 greater or equal to 0. x5, you have no x5 coefficient here, so that makes x5 greater, y2 greater or equal to 0. And x6, you have no coefficients here for x6, so that makes y3 greater or equal to 0. So at the end, you know these y1, y2, y3 should be unrestricted, but since you have those slack variables, that will make them greater or equal to 0. Okay? So I apologize for skipping this part, but this is important. Okay, and we have the optimal solution. So if you solve the dual, you know that you need to get the same optimal solution as the primal. So this is the solution for the primal. It's the same solution. You can solve it using the simplex method, but in this part of the lecture, we're not focusing on solving the problem. We are basically focusing on analyzing the solution. So if you solve it, this is what you're going to get, this value. Does anyone remember? We got these numbers at some point in the primal where we were looking at the sensitivity analysis. These numbers show, 1 and 2 show it up somehow. Do you remember what those numbers mean? Those were the dual prices. So you're basically we're saying that if you added a extra unit of, I believe it was X2, you were adding a unit of profit. So if you go back to the past lecture, you will see that these numbers show up. So that those were dual prices. Okay? So the dual variables are telling you what are the dual prices for your problem. Okay, so let's look now changes affecting feasibility. So the feasibility of the current optimal solution is affected only if the right-hand side of the constraints is changed. By changing the right-hand side, what you're doing is modifying the available resources that you have. Okay? So right-hand side is basically the right-hand side of the constraints is telling you instead of having 60 hours, now you have 100. Okay? So that the feasibility of the optimal solution is affected only if you change that availability of your resource. You go from 100 hours of one resource and you go to 0, you know that the solution would be affected. And that could not be a feasible, your current solution or your current optimal solution might not be feasible anymore. This change requires recomputing the right-hand side of the tableau using the following formula. So in order to get the new right-hand side of the tableau in iteration I, you need to multiply the inverse in iteration I times the new right-hand side of the constraint. This is the type of formula that you need to put in your formula sheet. Okay? So to recompute the right-hand side of the tableau, you need this formula. Recall that the right-hand side of the tableau gives the values of the basic variables. Okay, so now let's look at two examples of changes that could affect the feasibility. So suppose that the company is increasing the daily capacity of operations 1, 2, and 3 to 600, 600, 640, and 590 minutes. So you want to know how will that affect your revenue. So let me go back to the problem here. Maybe it'd be good to have this formulation here. Maybe I can copy and paste that. Okay, so this is our problem. And what we're saying is, want to increase daily capacity of operations of operation 1, 2, and 3 to 600. So from 430 to 600, 640, and 590 minutes. So each operation will be increased. So this will become, okay? So how will this change affect the total revenue? So with these increases, the only change that will take place in the optimum tableau is the right hand side of the constraints. So we know that the only change that will take place in the optimal tableau is the right hand side of the constraint. And we can use this to get the new right hand side of the tableau for the optimal iteration. So that's what we're going to do here. So we have x2, x3, and x6 be equal to the inverse at that point of the tableau. And I'm gonna allow you to use the calculator in the exam, just in case that you need to compute something like this. You don't have to do it by hand. So if you want to bring your calculator, you can bring it to the exam. 140, 320, and 30. So since these are positive, the current basic variables x2, x3, and x6 remain feasible. Okay, so feasible basically means that you are satisfying the constraints. Since you know that x1, x2, and x3, all your variables need to be positive or greater or equal to 0. As long as they are positive, they remain feasible. Okay, so they stay feasible, and the associated optimum revenue is 3 times 0 plus 2 times 140 plus 5 times 320, and that is equal to this. So increasing the, and this is using the objective function here, so increasing your operations will increase your revenue. Remember, the revenue was $1,350. Of course, if you have more time or produce more units, your revenue should increase. And that's what you're seeing here. So by increasing the operation time, you're increasing your revenue because you're increasing your production. Okay? Let's look at situation number 2. And I think I'm going to have to wait. Let's see how far we can go before, because I need some time to discuss the review. So let's look at this second situation. Although the new solution is appealing from the standpoint of increasing revenue, the company recognized that its implementation may take time So another proposal shifts the slack capacity of operation 3, in which you have x6 equals 20 minutes, to the capacity of operation 1. How will this change the impact in the optimal solution? So what we are saying here is, let me go back a little bit here. So you know x6 is not part of your production schedule because your production schedule is only defined by x1, x2, and x3, which are your products. You're having a slack variable with the value, positive value here. That slack is consuming part of your resources. What you're trying to do is, since this is not adding a unit of production to your schedule, you want to move that time that you have available, that extra time that you have available, to one of the other operations. So I'm going to move those 20 units in the capacity of operation 3 to operation number 1, which basically is changing your right hand side. So the capacity mix of the three operations changes to 450, 460, and 400. So you're moving 20 units from operation 3, so it used to be 420, you're taking 20 units and you're putting those 20 units here in the first operation. So that's why this becomes 400 and this becomes 450. So the resulting solution is, let's do the same procedure, x2, x3, and x6. Take the inverse from the optimal tableau. Times the new right hand side, 450, 460, and 400, and this will become this 230 minus 40. Is that solution feasible? It's not feasible because x6 is less than 0. Okay, so there's a variable that is not positive. So the resulting solution is infeasible because x6 is less than 0. Okay, so from here you can find the optimal solution for having this right hand side. What this is telling you is that the current solution is not feasible. But that doesn't mean that you can find an optimal solution for that problem. The issue is, in order to find this, you need to perform a set of computations, basically an adaptation of the simplex algorithm. For the purpose of this class, we are not going to be dealing with that part of the simplex method, but we're gonna have a new course coming up next semester in which those topics are gonna be covered. What it's called is you can come up from here at this point of the tableau, you can find an optimal solution using what is called the simplex dual algorithm. But again, that's not part of this class. It's very time, requires a lot of time. So that's why we have that part of the course in this new course that is going to be taught by Dr. Nawal next semester. So if you're interested in this type of stuff, you can always take that class. So I guess there's more people that are considering now part of, well, if you enjoy math, and again, this type of material is difficult, it's hard, but if you are one of the few who master these type of topics, then you're going to separate yourself from most of the industrial engineers because it's hard. Not a lot of people want to go in depth, but if you're able to master these topics, then you will be able to get a lot of opportunities in the job. Okay, so that will open your doors to rail companies.